yesterday when we were talking about Bernoulli trials, we talked about independence, right? You have to have independent trials in order for them to be Bernoulli trials. But some of the things we talked about yesterday were kind of wishy-washy, and you didn't know if they're independent or not. So, for example, on D and E, we did these yesterday in class. We just kind of skipped over them. All right. D says we wish to predict the outcome of a vote on the school budget and poll 500 of the 3,000 likely voters to see how many favor the proposed budget. So in this case, we do have two outcomes, but we might be wishy-washy about if they're independent because they're all from the same school population or something. So that gets kind of confusing. Well, are they independent or not? How do we make that assumption? On E, a company realizes that about 10% of its packages are not being sealed properly. In a case of 24, is it likely that more than 3 are unsealed? Again, it's factory. Do we know that they're independent or not? So here's the rule of thumb. Okay? For Bernoulli trials, if that assumption of independence is violated, it's still okay to proceed as long as the sample is smaller than 10% of the population. Okay? So if you have a small enough sample, it wouldn't matter if they were independent or not, because it would be so small. There's no one way that one would affect the other. Okay, so for example, then if we go back down here, on D, there's 3,000 likely voters. That's the population. What's 10% of 3,000? 300. So is 500 less than 300? No. So we wouldn't be able to use Bernoulli trials for D because our sample size is not small enough. It's gotten too large that maybe one affects the other when you start taking people out of the population. On E, we have a case of 24. Do you think, this could be subjective, do you think the case of 24 is less than all the packages of this factory, whatever this is? It's probably less than 10% of all those, right? So we would say that that would be okay to assume it's independent. Okay? Now, if you have something that's obviously one affects the other, all right, one of your homework questions tonight is about luggage. I don't care how small your sample size is. If you have luggage and it's all on the same flight, is that luggage independent of each other? No, it's all on the same flight. All right, so there's some things you have to think about. But if you're in this like kind of scenario where, well, how am I supposed to know if it's independent or not? Like, how do I know these people are related, or how do I know this we can do this? Has to be less than 10% of the population. Okay, so that makes sense. So then on your homework last night, I think C, D, and E, you can go back over those later. Those all had to be probably based on that if it's independent or not, so we can go back and look at that. Some of them might have been independent, some might not have been, depending on this definition. Okay? All right. So we talked about the geometric model yesterday. We're going to talk about the binomial model today. It answers a different type of question. So you have to know the difference. Because tonight's homework, they're all going to be mixed together. So it's your responsibility to decide, is this a geometric probability or a binomial probability before you start it. So you make sure you do the right thing. There's a very clear distinction, but I'm just going to make sure that you realize that's all mixed together on the homework. Last night, I ensured that it was all geometric, so they didn't think about it. All right? So, here is an example. It says, assume that 13% of people are left-handed. If we select 5 people at random, find the probability of each outcome described below. So first of all, we need to make sure there's Bernoulli trials. Do we have 2 outcomes? Yes, left-handed or not, or left-handed and right-handed for that matter. Do we know the probability of both those outcomes? Yes, 13% are left-handed, so then we know that 87% are right-handed, so we've got those probabilities. And then we have to talk about if they're independent. So if you have 5 people, is that less than 10% of the population? Yes, 5 is less than 10% of everybody. So we would say that they're independent of each other. You have 5 independent human beings. Now, we're going to start reading through these. Not all of these are geometric. I just want you to be able to identify which ones are geometric and which ones are not. Okay? So think about which questions you could have answered yesterday. So A, the first lefty is the 5th person chosen. Could you have answered that yesterday? Yes, that is geometric. The first is the 5th. B, there are some lefties among the 5 people. Could you have answered that yesterday? No. Geometric is the first of something to happen, right? This is just saying there's some in 5. Not the first in 5, some in 5, right? What about C? The first lefty is the second or third person. Yes, we could have done that last night. D, there are exactly 3 lefties in the group. No. E, there are at least 3 lefties in the group. No. And then there are no more than 3 lefties in the group. No. Geometric is very specific in that it's asking about the first of something to happen. The first on a specific trial or the first in a number of trials. All right, so really looking at one thing, the first. The same thing goes with expected values and averages. If it's asking about expected value, you're looking for, on average, how often will it take to get to the first one? So, more questions here. Consider our group of 5 people from exercise 17. A says, how many lefties do you expect? That's not geometric. That's asking you how many you would expect out of 5, not how many you would see until the first one. All right? C says, if we keep picking people until we find a lefty, how long do you expect it will take? That's saying, how many people does it take until you get to the first one? So that's geometric. All right? The rest of these questions are all based on a binomial probability. So tonight on your homework, they're going to be mixed in like this. You have to read the question. Is it geometric? Is it binomial? And then go from there. All right? Now, I'm going to go through the binomial model maybe more in depth than you would like me to, but it's because it has the multiple choice questions are created, and I want you to make sure you see the formula. Generally, you're probably not going to use the formula. You're going to use your calculator. But because, again, sometimes the multiple choice question will set it up for you, and it says which of the following would calculate the probability for you, and it fills the formula in. So you need to know where it came from and how to fill it in. It's on the yellow formula sheet, so you just need to be familiar with it. All right? And then I'll show you how to do it in your calculator. So I'll go both ways. Okay? So, binomial models still have Bernoulli trials, because it's still based on success, failure. All right? So, in this case, binomial models are looking at the number of successes in a specific number of trials. So maybe it's looking for the probability that you have 2 lefties in a group of 10 people. The probability you have exactly 4 lefties in a group of 10 people. It's looking for the number of successes in a specific number of trials. Because of that, you have to have 2 parameters. You have to have the number of trials. If they don't give you that, you can't answer it this way. And you need to know the probability of success. All right? If you know those 2 things, you can answer these questions. Does that make sense? All right. Now, they're using the whole Tiger Woods cereal box situation still. Let's say they said they're looking for the probability of getting exactly 2 Tiger Woods boxes out of 5 boxes of cereal. You would assume that you would calculate that this way. If it's 20% Tiger Woods and 80% something else, then 20%, you got 2 successes, so 0.2 squared. Then 80% to the third, because there's 3 failures, right? That's what we kind of did yesterday. The problem is, with a binomial model, when you're doing an exact number of successes in a number of trials, the order matters. So because the order matters, you have to go through and calculate how many combinations of that could happen. So it's not just that easy. Okay, so because of that, you're going to have to use a combination first to figure out how many combinations there are, and then multiply this probability by that many combinations. Again, your calculator can do that for you. Just like yesterday, there's a geometric PDF-CDF, there's a binomial PDF-CDF. All right. But again, I want to make sure you see the formula. So, since order matters, you have to do a combination. You did combinations in Algebra 2. There's 2 ways of seeing that. You have n choose k, either written in parentheses or as in capital CK, still n choose k, showing that there's a specific number of combinations. You don't necessarily need to know this formula for how to find out with the factorials. Your calculator can do a combination for you. All right? So in this case, we're doing the whole Tiger Woods situation. We're looking for 2 successes out of 5 boxes, I'm going to show you really quickly where you can find combinations on your calculator. All right? So if you were going to use this instead of binomial, whatever. So 2 successes out of 5 boxes. N is your number of trials and K is number of successes. So we're going to have 5 trials choosing 2 successes. So you would go to your calculator. You need to put the number of trials in first, so 5. And then math, probability, it's number 3. It says NCR. We're choosing 2. There are 10 total combinations of 2 successes out of 5 trials. Does that make sense? All right, so that's the combination piece. So if you were going to do it that way, you could do it that way. Clay, I can try to find it later. We'll look it up. Fancy calculators. No, it doesn't always work that way. Okay? So then, to do the formula, we would take the 10 different combinations and multiply it by that probability we had earlier to get the probability of 2 successes out of 5 boxes. All right? So this is the formula you're going to see on the AP formula sheet. Right? Okay. It says, it labels them specifically. It says binomial probability, and then it tells you this. Except that our formula sheet probably doesn't use Q, because it never does. It'll have 1 minus P instead of Q, because it's the same thing. Okay? I'll show you the formula sheet in a second, but that is on there. Again, the reason I show that to you is because occasionally they'll give you a multiple choice question and it lays out all the information and it says which of the following formulas would correctly calculate the probability. I need to be able to understand this context of what that is. All right. 99% of the time you're going to use your calculator and not have to worry about the formula. But everyone clear about where it came from. Okay. So then here is your binomial probability information all summed up together. Again, it's the number of successes in a specific number of trials. You have to have Bernoulli trials. So you have to have 2 outcomes, the probabilities, independent. You have to know the number of trials. You have to know the probability of a success. It gives you, again, the formula. Here is also, this is also important. We get the expected value and the standard deviation for a binomial model. All right? So how many successes do I expect to have in a specific number of trials, and with what standard deviation? Both of these are on your formula sheet. You do not have to memorize them. You just have to know that they're there and know when to use them. Okay? So if they're asking you, like on that lefties question, we'll do it again in a second. It says, how many lefties do you expect in 5 trials? That's the average. N times P. N is the number of trials. P is the probability of success. And then with what standard deviation? The square root of N times P times Q. And again, Q is just the complement of P. All right? Those are on the AP formula sheet. So let's go through and actually do these problems. We talked about the lefties earlier. Right? We'll do the geometric ones too. That way we have to think about it all together. There is a binomial PDF and CDF on your calculator, so I'll give you the reference sheet for that so when we use it, we can look at that too. I don't know if these reference sheets help you or not, but at least you have something to look back at if you forget. Okay, so on the lefties question, we already talked about the fact that we have Bernoulli trials, so we know we can use geometric and binomial probabilities. We know that the probability of someone being left-handed is 13%, and we have 5 people selected at random. So here is N, and here is P, probably. Okay? So A, the first lefty is the 5th person chosen. We said earlier that's geometric. So we do what we did last night. If you were going to use your calculator, would you use PDF or CDF? PDF, because you're looking for a specific person. And so if you were going to do it by hand, you would do 0.87 to the fourth times 0.13. Right? Or you would do PDF. You'd get an answer. Right? CDF is cumulative, so it starts adding some of them together. So if it said the first lefty is in the first 6 people, that's what CDF does. It does the combination of it could be the first person, second person, third person, etc., etc. All right. We're going to go back to B because I want to do one that's more straightforward. C, the first lefty is a second or a third person. This is geometric. You can't use CDF for this. Why can't you use CDF for this? Is that saying, well, I'm looking at C. Why can't you use CDF for C? Second or third, CDF adds from the beginning. So if you did CDF, it would add the combination of being the first person and the second person and the third person, and you don't want the first to be the first. You're just looking at second and third. So you could do PDF for second and PDF for third and add them together. That would work. Right? So we'd have 0.87 times 0.13 plus 0.87 squared times 0.13. All right, you have second is the first, or third is the first. All right, let's do D. There are exactly 3 lefties in the group. All right, so exactly 3, that's binomial. Again, you could use the formula. I'm going to do this one time. I'm not going to do it again. We have 5 people, or 5 people. We want exactly 3 lefties. Right? So it means I have 3 successes and 2 failures. I'm not going to use the formula again. If I did the formula, I'd have 5, choose 3, times 0.13 to the third, times 0.87 to the second. It's 0.0166. I could also use binomial PDF in the calculator. All right? So we're going to use binomial PDF and CDF. You're in the same place you did yesterday. You go to second variables. You want to scroll up. Probably takes less time. It's like close to the top of the second page, but I think scrolling up takes less time. We're looking for exactly 3. So this isn't cumulative. We're not adding up possibilities. We're just doing one specific set of possibilities. We use PDF. And it asks for different amounts of things. It asks for the number of trials. Well, there are 5 people, so that counts as 5 trials. It asks for the probability of success. In this case, we're looking for lefties. So the probability of a lefty is 0.13. And then it adds the x value, and that means how many successes you want out of the 5. We want 3. So I get 0.0166. I should get the exact same thing as I got with the formula. I would assume you're going to use your calculator to do these. Okay? I get that. Questions about that one? All right, on E, F, and B, we're still using binomial, but it's going to be a little more complicated, and that's fine. It's good practice. So back up to B. There are some lefties among the 5 people. Some means there might be 1 lefty, or 2 lefties, or 3 lefties, or 4 lefties, or 5 lefties. All right? So some means 1, 2, 3, 4, 5. What's the only possibility I haven't talked about? There could be 0 lefties in the group. Right? So binomial, 0 is a possibility. I don't think for the first anything, right? So you could have nothing. So since it says there are some lefties among the 5 people, I think it would be easiest to do 1 minus the probability of there being 0 lefties, because that would give us the probability of there being 1, 2, 3, 4, or 5. Does that make sense? Your calculator with a CDF, it adds up from 0. So that's why I can't do up to 5 using CDF, because it would include this part that I'm trying to leave out. Okay, it only goes from on the number line from left to right. It goes from 0 and up. So we want to go to your calculator and do 1 minus the probability of 0 lefties. You could use PDF or CDF for that, because that's what CDF calculates. It starts at 0 and goes on up. So if you say 0, it's going to stay 0. It's actually a PDF question, though. So we get 0.502. There's about a 50% chance that there are some lefties in the group. On E, there are at least 3 lefties in the group. There's at least 3 lefties. That means there's 3 or 4 or 5, right? Your CDF function cannot do that for you, again, because it adds from 0. So I will need to do 1 minus again. It's an at least question. We did at least questions before. We always do 1 minus then too. So you do the 1 minus the probability that there is up to 2 lefties, and that will leave us the probability that there are 3, 4, or 5. So again, on your calculator, 1 minus. This time we have to use CDF because we want to go up to 2. So 5 trials, lefties 13% of the time, up to 2. So we get 0.018. Does that make sense? You wouldn't want to include 3 because you want at least 3. So you don't want to subtract that one off. And then lastly, there are no more than 3 lefties in the group. That means there could be 0, or 1, or 2, or 3, right? So we don't have to do any subtracting. This is a perfect binomial CDF question, because we're going from 0 to 3, and we're adding all those together. All right? So you binomial CDF. Still 5 trials. The probability of being lefty is still 13%. And we want up to 3. So we get 0.999. So probably there are no more than 3 lefties. Is 99.9%. That makes sense. Only 13% of the population is left-handed. There's probably a very large chance that there's no more than 3 in the group of 5. Okay? Questions about any of those? It's the same thing. PDF is only for specific, like one thing. So for geometric PDF, that was the first on the 5th. For binomial, it's number of successes out of 5. So exactly 3 out of 5, exactly 2 out of 5. That's PDF. CDF starts adding things together for you. So for geometric, you would say the first in the first 5. That's what CDF would do. For binomial, CDF does 3 in the, like, up to 3 in the first 5. So it starts adding things together for you. All right. This one asks you about means and standard deviation. So same group of people. How many lefties do you expect? That's just in general in your group of 5 people. So that's binomial. That's a binomial mean. So we expect n times p lefties. So there were 5 people times probably 0.13. Someone did that for me, I think, this morning. It was like 6.65 or something. Okay. So we'd expect, I know you can't have 0.65 of a person, but we expect 0.65 lefties in a group of 5. Okay? With what standard deviation? That's the square root of n times p times q. So that's 5 times 0.13 times 0.87. The square root of that. Clay's going to calculate it for me, so I'll just type it in. .75. Then on C, if we keep picking people until we find a lefty, how long do you expect it to take? That's a geometric expected value because we're going until we find the first one. So in that case, the mean is 1 over p. So that's 1 over 0.13, which is... So we would take about 7 people until we found the first one, on average. Questions about any of those? On the assignment tonight, you can go about doing some of these questions different ways. Like if it had started asking about right-handed people, I could have used the 0.87 as my p, right? So just keep in mind that there's these two probabilities. Think about what you're trying to actually do. So make sure you use the right p in your calculator. Okay? So the assignment, I'll put up here in a second. Let me stop this.